Hello everyone. Now our next chapter is stereochemistry of organic compounds. First, we will read the introduction. One of the most important characteristics of organic compounds is their ability to show isomerism. Isomers are compounds which have the same molecular formula but different chemical and physical properties. It is of two types. First is structural isomerism and second is stereoisomerism. Structural isomerism compounds having the same molecular formula but different structures, that is, different arrangement of the atoms within the molecules, are called structural isomers, and the phenomena is called structural isomerism. It is of six types. First is chain isomerism. Compounds having the same molecular formula but different arrangement of carbon atom within the molecules are called chain or nuclear isomers, and the phenomena is called chain or nuclear isomerism. For example, the formula C4H10 represents two isomerism, first N-butane, second 2-methylpropane. Similarly, the molecular formula C6H14 represents five isomerism. First N-hexane, second 2-methylpentane or isohexane, third 3-methylpentane, followed by 2,2-dimethylbutane and 2,3-dimethylbutane. Second is position isomerism. Compounds have the same structure of the carbon atom chain but differ only in the position of the multiple, that is double or triple bonds, or the functional group are called position isomers, and the phenomena is called position isomerism. For example, but 1-ene and but 2-ene are positional isomerism. Similarly, propane 1-ol and propane 2-ol are also positional isomerism. Third is functional isomerism. Compounds having the same molecular formula but different functional groups are called functional isomers, and the phenomena is called functional isomerism. For example, the molecular formula C2H6O represents the two following functional groups. First is alcohol, or we can say ethyl alcohol. Second is methoxymethane. We can also say it dimethyl ether. Similarly, the molecular formula C3H6O represents the following four functional groups. First, propanone means acetone, propanol, prop2-in-1-ol or methoxyethene. Further are more examples of this: carboxylic acids and esters, aldehydes and ketones, dienes and alkynes, alkanes and alkynes, nitroalkanes and alkyl nitrile, primary, secondary, and tertiary amines, aromatic alcohols, phenols, and the ethers are also the example of functional groups. It may be, however, be noted that orthocresol, metacresol, paracresol are themselves positional isomerism. Fourth is metamerism. Compounds having the same molecular formula but different number of carbon atom or alkyl groups on either side of the functional group are called metamers, and the phenomena is called metamerism. Metamerism occurs among the same number of the same homologous family. For example, ethoxyethane is a metamer of 1-methyl methoxypropane and 2-methyl-oxypropane. Similarly, pentane 3-on is a metamer of pentane 2-on and 3-methylbutane 2-on. It may be noted here that metamers may also be the position isomerism. For example, pentane 2-on and pentane 3-on may be regarded as position isomers as well as metamers. Fifth is tautomerism. It arises due to 1,3 migration of hydrogen atom from any polyvalent atom to the other within the same molecule. Isomers thus obtained which exist in dynamic equilibrium with each other are called tautomers, and the phenomena is called tautomerism. There are several types of tautomerism, but ketoenol tautomerism is the most important. In this type of tautomerism, one form tautomer contains the keto group while the other contains the enolic group. The two simplest examples of ketoenol tautomerism are acetaldehyde and acetone. In simple aldehyde and ketones, that is acetaldehyde or acetone, etc., the amount of enolic form is negligible small. However, if the enolic form is stabilized by intramolecular hydrogen bonding, that is chelation, such as in 1,3-dicarbonyl compounds, the amount of enolic form is much greater than in acetaldehyde or acetone. For example, in acetic ester, the amount of enolic form is 7%. Similarly, acetyl acetone also exhibit ketonal tautomerism, but the amount of phenolic foam here is much higher than even in the acetic ester. This is the the reason that keto group is a much better electron withdrawing group than the ester group. Now we will do the essential condition. For an aldehyde to exhibit ketonal tautomerism, it is essential that it must have at least one alpha hydrogen. The acetophenone, butane, 2-on propanaldehyde all contain alpha hydrogen atoms and hence show tautomerism. In contrast, benzaldehyde, benzophenone, etc. do not show keto-enol tautomerism because they do not contain any alpha hydrogens. Similarly, nitro compounds also show tautomerism. Next and last is ring chain isomerism. Compounds having the same molecular formula but possessing open chain or cyclic structures are called ring chain isomers, and the phenomena is called ring chain isomerism. For example, C3H6 represents as propene and cyclopropane, which are ring chain isomerism. Similarly, but2-ene and 2-methyl-prop-1-ene are ring chain isomerism. Cyclobutane and methyl chloropropane. Now our next topic is stereoisomerism. Isomers which have the same structural formula but have different relative arrangements of atom or groups in a space are called stereoisomers, and the phenomena is called stereoisomerism. Stereoisomers are of following two types. First is conformational isomers and second is configurational isomerism. Let's study one by one. First is conformational isomerism. Stereomers which differ in the relative position of atoms within the molecules and which can be converted simply by rotation about sigma bonds are called conformational isomers. In other words, the interconversion of these isomers does not require breaking and remarking of covalent bond. Second is configurational isomers. Stereoisomers which can be interconverted only by breaking and remarking of covalent bonds and not simply by the rotation about sigma bonds are called configurational isomers. Configurational isomers are also following two types. First, optical isomerism and second, geometrical isomerism. First, we will study about optical isomerism. Certain compounds can exist in two stereoisomeric forms which cannot be superimposed on one another. In spite of this difference in the relative spatial arrangement of atoms, these isomers have identical physical properties such as melting point, boiling point, refractive index, density, solubility, etc. They resemble one another in most of their chemical reactions. However, they differ only in their behavior towards plane polarized light. One rotates the plane polarized light towards right, but other rotates towards left, but to the small extent. Such a compound are called optical isomers, and the phenomena is called optical activity. Now we will do some general concept about optical isomerism. In order to understand the phenomena of optical isomerism, we must be familiar with the following terms. First is plane polarized light, or we can also say that it is PPL. Ordinary light consists of electromagnetic waves of different wavelengths. Monochromatic light, on the other hand, consists of waves of only one wavelength. It can be obtained either by passing the ordinary white light through a prism or grating or by using a source which gives light of only one wavelength. For example, sodium lamp emits yellow light of about 589.3 nanometer wavelength. Whether it is ordinary light or monochromatic light, it consists of waves having vibration in all the planes perpendicular to the line of the propagation of light. If such a beam of light is passed through a nickel prism, the light comes out to the prism has vibration only in one plane. Such a beam of light which has vibration only in one plane is called plane polarized light. The nickel prism used to obtain plane polarized light is called a polarizer. Second is angle of rotation. The angle through which the plane of polarized light gets rotated on passing through the solution of an optically active compound is called the angle of rotation. It is denoted by the Greek letter alpha. Third is polarimeter. The instrument used for measuring the angle of rotation of the plane polarized light is called the polarimeter. It consists of light source, two nickel prisms and polarimeter tube. The nickel prism near the light source is called the polarizer, while that near the eye of the observer is called the analyzer. The axis of polarization of the polarizer is fixed while that of the analyzer can be changed. And between the polarizer and the analyzer is placed a glass tube called the polarimeter tube, which contains the solution of optically active substances. The solid line represents the plane of polarized light before, and broken lines represent after passing through the solution of an optically active substance. If the axis of polarization of two nickel prism is held parallel to each other and the polarimeter tube is empty, the plane polarized light from the polarizer passes through the analyzer without any change in intensity. Conversely, if the two nickel prisms are held with their axis of polarization perpendicular to each other, no light passes at all. This angle through which the analyzer has to rotate it to get the maximum transmission of light is called the angle of rotation. The angle of rotation means alpha of an optically active compound depends upon the following factor. First, nature of optically active substance. Second, concentration of the solution in gram per milliliter. Third, length of the solution through which the light passes. Next, nature of the solvent. Fifth is wavelength of the monochromatic light used. Sixth is temperature of the sample. Now our fourth term is specific rotation. In order to compare the rotatory power of different optically active substances, optical activity is usually expressed in terms of specific rotation. The specific rotation of an optical substance is defined as the degree of rotation observed when the plane polarized light is passed through a tube having a path length of 1 decimeter and a concentration of 1 gram per milliliter of a compound at a specified temperature and wavelength. It is denoted by lambda Td, where T is the temperature and D is the wavelength of the light. Usually D line of sodium having a wavelength of 589.3 nanometer is used as a source of monochromatic light. Since it is not possible to dissolve 1 gram of optically active substance in 1 ml of the solvent, therefore the measurement of the angle of rotation is usually carried out at lower concentration. The specific rotation is then calculated by the application of the following equation. Bracket concentration of lambda T is equals to observed angle of rotation divided by L into C, where L is the length of the polarimeter tube in the decimeters and C is the concentration of the substance in the gram centimeter cube. Our next is optical activity and discovery. The phenomena of optical activity was discovered by French chemist Louis Pasteur in 1848. He observed that when a concentrated solution of sodium ammonia tartarate was allowed to crystalline, two types of crystals separate out. Working carefully with a magnifying glass and pair of tweezers, Pasteur was able to separate the crystal into two pills, one of right-handed and other of the left-handed crystals. Each type of crystal, when dissolved in water, was found to rotate the plane of polarized light. One solution rotates the plane of polarized light towards right, while the other solution rotates towards left, but to same extent. Later on, millions of molecules have been discovered which rotates the plane of polarized light. Such substances which can rotate the plane of polarized light are called optically active substances, and the property of a substance to rotate the plane of polarized light is called optical activity. A substance which rotates the plane of polarized light towards right, that means clockwise direction, is called dextrorotatory and is usually represented by D or plus. On the other hand, a substance which rotates the plane of polarized light towards left, or we can say in anti-clockwise direction, is called levorotatory and is usually represented by small l or minus sign. Next is chilarity. An inspection of the molecular structures of optically active compounds indicates that all these have chiral or disymmetric molecules. A molecule is said to chiral or disymmetric if it is not superimposable on its mirror image, and the property of non-superimposability is called chilarity. On the other hand, a molecule which is superimposable on its mirror image is called achiral or non-symmetric or non-disymmetric or symmetric. To understand the terms chiral and achiral, let we consider the alphabet P and A. Whereas P is chiral and A is achiral as shown in the figure 3.3. Our next topic is elements of symmetry. The superimposability of an object and its mirror image can be tested with the help of three elements of symmetry, such as plane of symmetry, or center of symmetry, or an alternating axis of symmetry. Chiral objects do not have an element of symmetry. On the other hand, achiral objects have at least one or more elements of symmetry. First is plane polarized light or mirror plane. The most commonly observed element of symmetry is a plane of symmetry or mirror plane or sigma plane. It is defined as an imaginary plane which divides a molecule into two equal halves such that one half of the molecule is a mirror image of the other. Like objects, some molecules also possess plane of symmetry. For example, 2-chloropropane has a plane of symmetry which is perpendicular to the plane of the paper and passes through Cl, C and H atoms. Similarly, mesotartaric acid has a plane of symmetry which is perpendicular to the plane of the paper and passes through a midpoint of carbon-carbon bond. Therefore, both these molecules are achiral since they can be superimposed on their respective mirror image, hence are optically inactive. On the other hand, molecules of 2-butanol and lactic acid do not have a plane of symmetry, hence are chiral. As a result, they cannot be superimposed on their respective mirror image and hence they are optically active in nature. Second is center of symmetry. A center of symmetry is defined as a point from which lines, when we draw on one side and produced on equal distance on the other side, will meet identical points. It is also called center of inversion and is usually denoted by CT. For example, both trans 1,3-dimethylcyclobutane and mesotartaric acid have a center of symmetry, hence are optically inactive. Third is alternating axis of symmetry. A molecule is said to possess as n-fold alternating axis of symmetry if rotation through an angle of 360 degree by n about this axis and then followed by reflection in a plane perpendicular to the axis gives a molecule which is indistinguishable from the original molecule considered. For example, the molecule A as shown in the figure 3.31. Here Z positive and Z negative represent chiral groups such as positive CH3, CH3, C2H5 and C minus CH, CH3, CH2, C2H5 respectively. Rotation of a molecule A through 90 degree about axis AB which passes through center of the ring and perpendicular to the plane gives molecule B. The reflection of B gives the original molecule A. Thus, this molecule has fourfold 360 degree by 9 is divided by 4 fold alternating axis of symmetry and hence is a chiral. Since a one-fold alternating axis corresponds to the plane of symmetry, two-fold alternating axis corresponds to center of symmetry. Therefore, absence of alternating axis of symmetry is the necessary and sufficient condition for a molecule to exhibit optical activity. Now, next is a relationship between asymmetry, dissymmetry, and chirality. It is interesting to note that while describing optical activity of organic compounds, two terms asymmetry and dissymmetry have been used without any distinction, yet there exists a subtle difference between them. A molecule which has no element of symmetry is called asymmetric molecules. Such a molecule is usually optically active. On the other hand, a molecule which has no alternating axis of symmetry but may or may not have a simple axis of symmetry is called dissymmetric molecule. Like as asymmetric, dissymmetrical molecules are usually optically active. Considered, for example, 2-butanol, it has no plane of symmetry. That is, it is an asymmetric molecule and hence is optically active. Now consider the projection formula of optically active tartaric acid. It has simple axis of symmetry in the center of the molecule. It is shown by dot and passes perpendicular to the plane of the paper. Rotation through 180 degree about this axis gives formula second which coincides with the original formula. Thus, optically active tartaric acid has a simple or C2 axis of symmetry. Hence, it is not a symmetric molecule but it is a dissymmetric molecule. To avoid this confusion, another term called chilarity has been introduced and is more widely used these days. It simply relates optical activity with the non-superimposable mirror image relationship, and note the absence of elements of symmetry. Thus, a molecule is said to be chiral and hence optically active if its mirror image is non-superimposable. Okay, now our next topic is stereogenic center or stereocenter. We have stated above that tetrahedral carbon atoms attached to four different atoms or groups are called asymmetric or chiral carbon atom. However, in 1894, M. Michelot and J. Cecil pointed out the use of these terms chiral carbon atom has created conceptual confusion. According to the scientists, it is not the atom which is chiral, but actually is the molecule which is chiral. In other words, chilarity is a geometrical property which provides, extends, and affects all the parts of a molecule. For example, all the atoms of butane 2-ol are in the chiral environment, hence all are said to be chiralotropic. However, we have not used the chiral atoms such as C2. Further, consider the cis and trans stereoisomers of 1,3-dichlorocyclobutane. Here, carbon atom 1 and 3 are centers of diastereoisomerism but are not chiral centers since they have two identical groups. Therefore, these are preferably called as centers of diastereomers or stereogenic center. The stereogenic centers may or may not be chiral. For example, stereogenic center in C2 and 2-butane all is chiral, but C1 or C3 in cis or trans 1,3-dichlorocyclobutane is chiral. Thus, all the chiral centers are stereogenic, but all the stereogenic centers are not chiral centers. Therefore, in this unit, filter, we shall use the term stereocenter or stereogenic is instead of chiral center. Now, next is configurational and fixture projection. Stereoisomers have the same molecular structure but different relative arrangement of atoms or groups in the space. The spectral arrangement of atoms or groups which characterizes or defines a particular arrangement is called its configuration. The configuration of organic molecule can be best visualized by inspection of their modes of three-dimensional structure. Depending upon how you hold the molecule, the 3D structures of an organic compound may be represented in a number of ways, but the most commonly used 3D model is flying wedge model. And this model, three types of lines are used. A solid wedge, thick solid line represent a bond line above the plane of the paper projecting towards the observer. Ordinary solid lines dash represent a bond line within the plane of the paper, while the dotted wedge represents a bond line below the plane of the paper or away from the observer. In this method, sometimes the dotted wedge is placed by a dotted line for the purpose of simplicity. However, it is not always convenient to construct these models or draw their 3D structures. It therefore becomes necessary to devise a method to present three-dimensional structures on two-dimensional surface such as paper or a blackboard. In 1891, a German chemist Emil Fischer introduced a simple method to represent the spatial arrangement of atoms or group around chiral centers on a paper. These planar representations are called Fischer projection. The main points of his process are as are given below. First, the molecule of any chiral carbon compound containing the chiral center which is viewed in such a way that the groups attached to the chiral center are horizontal and pointing towards the observer, while the other two are vertical or pointing away from the observer. Second is the various atoms or group attached to the chiral center are then projected on the plane of the paper in the front of a cross. By convention, the chiral center is not shown, but it is believed to lie at the intersection of horizontal and the vertical bonds. Third is if the chiral molecule contains two or more chiral centers, each chiral center must be viewed individually in the manner described above. Fourth is as far as possible, the vertical part of the projection formula thus obtained should represent the longest chain of the carbon atom, which is the most oxidized carbon at the top. This carbon atom is numbered according to the IUPAC nomenclature. Depending upon which bonds are drawn in the horizontal and which bonds are drawn in the vertical position, several fixture projections can be written for the same compounds. Therefore, necessary to compare two different projections to see whether they are represent the same or different compounds. To test the identity of different fixture projection for the same compound, the following rules must be observed. First, a fixture projection must be lifted from the plane of the paper and turned over. Such operation gives the enantiomer of the original molecule. For example, structure 1 and structure 2 represent the enantiomer of bromochlorofluoromethane. Second, a fixture projection may be turned through 180 degree in the plane of the paper. Such an operation gives the same stereoisomers. Third, a fixture projection should not be turned over 90 degree or 270 in the plane of the paper. Such an operation gives enantiomer of the original molecules. Fourth is, one may interchange the group attached to the chiral carbon an even number of times in a fixture projection without affecting the configuration of the molecules. It may be noted that the number of interchanges should be even no matter which groups are exchanged. A useful corollary of this rule is that we can hold any one group steady and rotate the three in either clockwise or an anti-clockwise direction. For example, if the COH group in the Fischer projection for aniline is fixed and the other three groups rotated in the clockwise direction, the projection thus obtained are identical and represent the same stereoisomer of alanine. Next is optical activity. All the optically active compounds exist in two or more stereoisomeric forms which differ from one another in the relative spectral arrangement of the atoms of the group. These stereoisomers, which resemble one another in their chemical reaction and most of the physical properties but differ only in the behavior towards ppl, are called optical isomers, and the phenomena is called optical isomerism. Optical isomers in compounds containing one chiral center or stereogenic center, that is enantiomers. Optical isomers which are non-superimposable mirror images of each other are called enantiomers, and the phenomena is called enantiomerism. The enantiomers have identical physical and chemist properties but rotate the ppl in opposite direction but to small extent. To understand the phenomena of enantiomerism, let us again consider the molecules of bromochlorofluoromethane. It exists in two stereomeric forms, first and second, which are non-superimposable mirror of each other. Further, each of the two isomers is optically active and rotates the ppl in the opposite direction but to small extent. The enantiomer which rotates the ppl towards right is called dextrorotatory and is represented by small d or plus sign, or which is rotate the plane of polarized light towards left is called levorotatory and is represented by small l or minus sign. However, it may be emphasized here that it is not possible to tell which isomerism is dextro or levo just by looking at the structure. It has to determine experimentally. Similarly, lactic acid and butane both show enantiomerism since their molecules cannot be superimposed on their mirror image. Conditions for enantiomerism. It may be noted that the necessary and sufficient condition for a molecule is to exhibit enantiomerism is chilarity and dissymmetry of the molecule. The molecule and its mirror image must be non-superimposable. It may or may not contain chiral or asymmetric carbon atoms. Usually, the presence of one or more chiral carbon atom causes the molecules to show enantiomerism and hence optical activity, but certainly it is not necessary and sufficient condition. This is due to the reason that it contains a plane of symmetry which divides the molecule into two equal halves so that the half of the molecule is a mirror image of other. As a result, mesotartaric acid is a mirror image acid and its mirror image are superimposable. In other words, mesotartaric acid is an achiral or non-disymmetric or symmetric molecule and it does not show enantiomerism or optical activity. Thus, the optical inactivity of mesotartaric acid is due to the internal composition, that is, the rotation caused by one half of the molecule is exactly cancelled by the unequal and opposite rotation caused by the other half of the molecules. On the other hand, there are many molecules which do not contain chiral carbon atoms, but their molecules are chiral or disymmetric and show enantiomerism or optical activity. For example, aniline and ortho disubstituted diphenyls do not contain chiral carbon atoms, but their molecules are non-superimposable on their respective mirror image, hence show enantiomerism or optical activity. Now we will do the properties of enantiomerism. First, they have identical physical properties such as melting point, boiling point, densities, solubility, refractive indexes, etc. They differ only in the direction of rotation of the plane polarized light. One rotates the PPL towards right and the other rotates left but to a small extent. Second, enantiomers have identical chemical properties except towards optical activity region. Third, enantiomers have different biological properties. This difference in reactivity of enantiomer is of great importance in biochemistry and chemistry taking place in our body. Now next is chiral or achiral molecules with two stereogenic centers or optical isomerism in compounds containing two stereogenic centers. So far we have discussed that the presence of one stereogenic carbon makes the molecule dissymmetric or achiral. As a result, compound containing one stereogenic center can exist in two stereoisomerisms known as enantiomers. Therefore, it is expected that compounds which contain two or more stereogenic would exist in more than two stereoisomeric forms. To examine this, let us now discuss the optical isomerism of compounds containing two stereogenic centers. These two stereogenic centers can be dissimilar or similar. Two representative examples of such compounds are 2,3-dichloropentane and tartaric acid. Let us now discuss the optical isomerism in each one of them separately. First, compounds with two dissimilar stereogenic center, that is diastereomers. Compounds such as 2,3-dichloropentane which contain two dissimilar stereogenic centers and hence can exist in four stereomeric forms which are all optically active. Stereoisomers first and second are non-superimposable mirror images of each other, hence represent a pair of enantiomer. One of these enantiomer is dextrorotatory while the other is levorotatory. Likewise, stereoisomerism third and fourth are non-superimposable mirror images of each other and hence represent another property of enantiomers, one dextrorotatory and other levorotatory. Thus, compounds containing two dissimilar stereogenic centers exist in four optical isomers, which can be regarded as two pairs of enantiomers. Now, the question arises as to what is the relationship between any two pairs, such as one and third, first and fourth, second and third, or second and fourth. An inspection of their structure reveals that none of these pairs are mirror images of each other, nor can be interconverted by rotation about carbon-carbon. Such stereoisomers are not mirror image of each other, are called diastereomers or simply diastereomers. Thus, one and third, one and fourth, second and third, second or fourth, all represent a pair of diastereomers. In other words, diastereomers are stereomers which are not enantiomers. They have the same configuration at one stereo center or the chiral carbon but different at their convenience. Yourself by examine their structure. Now we will do the properties of diastereomers. First, physical properties: melting point and boiling point. Unlike enantiomers, diastereomers have different physical properties such as melting point, boiling point, solubilities in a given solvent, densities, refractive index, etc. Second is separation. Due to their difference in physical properties, diastereomers like enantiomers can be separated by physical methods of separation such as fractional distillation, crystallization, fractional distillation, chromatography, etc. Behaviors towards PPL. Diastereomers may be either optically active or inactive. For example, geometrical isomers which are also regarded as diastereomers are optically inactive, while others are usually optically active. Even the optically active diastereomers may have some same or opposite signs of rotations. Third is chemical properties. Unlike enantiomer, diastereomers have similar but not identical chemical properties. Thus, the rate of the reactions of diastereomers with chiral or achiral reagents are generally different. This is due to the reason that neither the reagents nor the transition states are mirror image of each other. As a result, diastereomers have different angles of different energies of activation for a particular reaction and hence react at their different rates. Calculation of number of stereoisomers, that is optical isomerism and mesoforms. The total number of stereoisomers depends upon the nature of the molecule and the number of stereogenic centers it contains. The following cases arise. First, when the molecule is unsymmetrical and contains n stereogenic centers or chiral carbon atoms. Number of optical isomerism is 2 raised to power n. Total number of mesoforms is equals to 0. So the total number of isomerisms is called 2 raised to power n. When the molecule is symmetrical and has even number of stereogenic center or chiral carbon atom, the number of stereoisomers is calculated as follows. Number of optical isomers 2 raised to power n minus 1 and number of mesoforms 2 raised to power n by 2 minus 1. So total number of stereo isomers is 2 raised to n की power n by n minus 2 divided by 1. When the molecule is when the molecule is symmetrical and has odd number of stereogenic center. So the number of optical isomers is equals to 2 raised to power n by 2 minus 1 by 2. Number of mesoforms 2 raised to power n divided by 2 minus 1 by 2. So the total number of stereoisomers, that is meso plus optical isomerism, is equals to 2 raised to power n minus 1. Now we will do prochirality and prochiral molecules. An carbon atom in a molecule is called prochiral if the replacement of one of its hydrogen atoms by a substituent atom or a carbon produces a chiral center. For example, C2 in propanoic acid is prochiral since replacement of one H atom at C2 by bromine produce a chiral molecules. Molecules which contain prochiral centers are called prochiral molecules and the phenomena is called prochirality. Now next is relation and inversion of configurations. Whenever a chemical reaction is carried out on a chiral molecule, the product may have the same configuration as the reactant or may have the opposite configuration. If the configuration of the reactant and the product same, the reaction is said to be proceed with retention of configuration, and the configuration of the product is opposite to that of the reactant, the reaction is said to proceed with inversion of configuration. The two cases arises. First, when the bond to the stereocenter or the chiral center atom is not broken, but the reaction takes place at some other side in the molecule, the configuration of the reactant is retained to the product. Second, when the bond to the stereocenter or the chiral center is broken, either the inversion or the retention of the configuration may occur as discussed below. Inversion. In SN2 reaction, the attack of nucleophile always occurs from direction opposite to the leaving group. As a result, all SN2 reactions are accompanied by inversion of configuration. This phenomena was first discovered by Walden and hence it is also called Walden inversion. Second is retention. Two important ways in which retention of the configuration may occur as discussed below. First, if two SN2 reactions occurs at same stereocenter, one after the other, the configuration of the final product is the same as that of the starting material. The retention of the configuration has explained on the basis of neighboring group participation, in which the oxygen of the carboxylate ion first helps to eliminate Br2 negative in SN2 reaction to form alpha lactone, which is subsequently undergo SN2 reaction by the OH ion at the same stereocenter to afford lactate ion, which complete retention of the configuration. If, however, the reaction is carried out in the presence of a strong alkaline solution, the hydroxide ion compete with carboxylate ions and normal SN2 reaction occur to give lactate with inversion of configuration. Second, retention of configuration may also occur if the bond cleavage and bond formation occur at the face of the chiral molecules. For example, chiral alcohols react with thionyl chloride to give chlorosulfides, which subsequently decompose to form alkyl halides with the retention of configuration. Thus, it is an example of SN1 reaction. It has been suggested that SN1 mechanism can proceed via ion pairs, lone pairs, and H1 below. And now this is racemic modification or racemic mixture. When equal amounts of two enantiomers are mixed together, it gives an optically inactive form called the racemic mixture or racemic modification. Is denoted by the prefix plus or minus or Rx or DL before the compound. For example, two equal amounts of plus lactic acid and minus lactic acid are mixed together. We get the racemic mixture, or plus minus or RS is the lactic acid. A racemic mixture is always optically inactive because the rotation caused by the molecule of the one enantiomer are exactly cancelled by equal and opposite rotation caused by the same number of the molecules. The other physical properties of racemic mixture such as melting point, boiling point, solubility in a given solvent, etc. are also different from those of enantiomers. For example, the melting point of either enantiomer of lactic acid is 326, while that of racemic mixture is just 291 Kelvin. Racemization: the process of converting of one enantiomer of an optically active compound into the racemic mixture is called racemization. Racemization can occur either by heat, chemical reagents, or even by the contact with the polar solvent. Some of the more important mechanisms by which racemization usually occurs are discussed below. First, by rotation about carbon-carbon single bond. The optical activity of orthosubstituted diphenyl is due to the restricted rotation about the carbon-carbon single bond joining the two phenols. The cause of this restricted rotation is presence of bulky substituents at the ortho position of the two phenyl groups, which prevents them in assuming the planar transition state. These compounds undergo racemization on heating. Second, by enolization. Optically active aldehydes or ketone having alpha hydrogens on the carbon atom undergo racemization on treatment with the acid and the base. Third, by SN1 reaction, racemization of an optically active secondary halide such as 2-chlorobutane occurs when treated with Lewis acid such as AlCl3. Under these conditions, the alkyl halide first undergo ionization by SN1 process to form carbocation. Being planar, the recombination of the carbocation with the halide on can occur from either side with equal probability in resulting in the racemization. Fourth, by SN2 mechanism, optically active halides having the halogen on the carbon can also undergo racemization by SN2 mechanism. For example, when a solution of plus or minus 2 iodobutane is treated with NaI in acetone, it undergoes racemization to give plus minus 2 iodobutane. Next is resolution. As stated above, racemic mixture contains equal amounts of two enantiomers. This process by which racemic mixture can be separated out and its plus and minus enantiomers is called resolution. Since the enantiomers have identical physical and chemical properties except towards optical activity reagents, they cannot be separated by the usual techniques such as fraction crystallization, fractional distillation, chromatography, etc. Therefore, special methods are used to achieve their separation. Some of the methods to resolve racemic mixture as discussed below. First is a mechanical separation. This is the most classical method and was used by Petrov to separate the enantiomers of sodium ammonium tartrate. Sometimes, when a concentrated solution of racemic mixture is allowed to crystallize, two types of crystal may separate, one type being mirror image of the other. These two types of crystallines can be separated by hand picking using a pair of tweezers and magnifying glass or the microscope. Limitation: this method is not laborious and time consuming and is applicable to only those compounds which give well defined crystal of enantiomers, so they cannot be easily be distinguished. Second is biological chem method. Contain microorganisms use one enantiomer as their food, leaving out the other. For example, Penicillium glacium consumes only the plus tartaric acid. Thus, racemic tartaric acid can be resolved by adding Penicillium glacium, to which the consumes plus tartaric acid and leaving behind minus tartaric acid. Similarly, there is a chemical method. This is the most widely used method for separating racemic mixture. This method is based upon the principle that when a racemic mixture is treated with an optically active reagent, It gives a mixture of two diastereomers. Since diastereomers are not mirror image of each other, they have different physical properties such as melting point, boiling point, solubility, etc. Hence, can be separated by their physical methods such as fractional distillation, fractional crystallization, etc. After the separation, each diastereomer is decomposed separately to give a mixture of two corresponding enantiomers and optical reactive reagent. The optically reactive reagent is then removed by suitable method, leaving behind the pure enantiomer. To illustrate this method, let us consider the resolution of plus minus tartaric acid when treated with an optically active base such as plus brucellin plus minus tartaric acid give a mixture of two diastereomers plus tartaric acid and plus minus tartaric brucellin acid. These two compounds being diastereomers which have different solubilities and hence can be separated by fractional distillations. After the separation, each diastereomer is purified by recrystallization and treated separately with dilute HCl to generate the corresponding tartaric acid. The whole process systematically, which is shown in the below. Fourth is chromatography. By chromatography, we can also separate this. Next is DL and RS nomenclature, that is relative and absolute configuration. The arrangement of the atoms or group of atoms which characterizes a particular stereoisomer is called its configuration. The two terms which are commonly used to describe the configuration of different stereoisomers are absolute and relative configuration. By absolute configuration, we mean the actual arrangement of atoms or group of atoms in a space of a particular stereomer of a compound. The relative configuration, on the other hand, means the arrangement of the atoms or a group of atoms in space of a stereoisomer of a compound relative to the atoms or group of atoms of another compound chosen as arbitrary standard. If the absolute configuration of the standard is established by some unambiguous method, then the relative configuration of the stereoisomer is correlated and this represent the absolute configuration. Now we will do DL or RS system. Before 1951, there was no method available for determining the absolute configuration of a compounds. Therefore, the relative configuration of all the compounds were established with respect to glyceraldehyde chosen as the arbitrary standard. The two enantiomers of this compound were designated by D and L symbols. The plus enantiomer was given by the symbol capital D and was assigned to the configuration third in which OH group lies towards right and H atom lies toward left. The CHO group lies at the top and CH2H lies at the bottom of the Fischer projection. On the other hand, minus glyceraldehyde was given the symbol capital N and was assigned as configuration fourth in which the OH group is towards left and H atom towards the right. The relative configuration of compounds were then established. Any compound that can be prepared from or converted into D-glyceraldehyde which belong to D series, and similarly any compound which can be prepared from or converted into L-glyceraldehyde will belong to L series. These correlations are based upon the general principle that if a reaction does not involve the cleavage of a bond to the chiral center, the configuration about that chiral center is retained. For example, D plus glyceraldehyde can be interconverted into minus glyceric acid by simple oxidation, and hence the configuration of glycerolic acid thus obtained must be D. Although the configuration assigned by Fischer to D and L glyceraldehyde was purely arbitrary at the time, but subsequently in 1951 X-ray diffraction studies on sodium rubidium tartarate by Bijovite proved that they were in fact correct. Thus, the configuration of D minus glyceric acid and L plus lactic acid discussed above in fact represent the absolute configuration. It may be here noted that there is no simple relationship between the absolute configuration of a particular enantiomer and the direction of the rotation of the ppl. In other words, compounds having the same configuration may have different signs of relations. For compounds containing several chiral carbon atoms, the configuration at one stereocenter is related to glyceraldehyde with the configuration at the other stereocenters are determined relative to the first. Limitations of this. Sometimes the same compounds can be correlated by the sequence of reactions to non-D compounds and by different sequence of reactions to non-L compounds. Second, this method is quite cumbersome to apply to such compounds which contain two or more chiral carbon atoms. Because of their difficulties, D and L system is seldom used these days except for carbohydrates and amino acids. Now we will do D or S, that is obsolete configuration. The limitation of DL system have however been removed by an unambiguous system developed by RS Chen England, CK England, YP Prelog Switzerland called CAN England Prelog CIP system or simply the RS system. The designation of the absolute stereochemistry of an optically active compounds according to the system involves the following step. First, a priority number such as 1, 2, 3 and 4 is assigned to each of the 4 atoms or a group of carbon atom attached to the chiral center in accordance with the following sequence rule. First rule is, if the 4 substituents attached to the chiral carbon are all atoms, their priority numbers are decided on the basis of their atomic number. The atom of higher atomic number gets a higher priority, this from the compound. Bromochloride diiodomethane is the order of decreasing priority. I is equals to first, Br is equals to second, and C is equals to third, and H is equals to fourth. If the two atoms attached to the chiral carbon are isotopes of same elements, the isotopes of higher mass number gets the higher priority. Second sequence rule, if the relative priority of the two groups attached to the chiral carbon cannot be decided on the basis of first rule, it may be decided by comparing the atomic numbers of next in the group and so on, if necessary, working outwards from the chiral carbon to the point of the difference. In other words, if the first carbon atom attached to the central atom is same in both the groups, compare the atomic number of the other carbon atoms to each of these first atoms. Third sequence rule is, double bond and triple bonds are treated as if they have duplicate or triplet singles bonds. In other words, double bond each double bond atom is duplicated and each triply bonded atom is triplicated. Thus, to illustrate this, let us consider glyceraldehyde and 3-chloropentane as an example. Next is comparison of priorities of phenyl, acetyl, ethynyl or vinyl and isopropyl groups. In order to assign priorities of this group, let us consider the number and nature of atoms attached to the first carbon atom in each case. In phenyl and acetylene groups, the first carbon is connected to 3 other carbon, while in vinyl and isopropyl, the first carbon is connected to only 2 carbon atoms. Therefore, phenyl and acetylene groups have higher priority over vinyl and isopropyl groups. To decide the relative priorities of phenyl and acetylene group, we must proceed further along the chain. In phenyl group, 2 of its CCC are further connected to CCH, while the third is a duplicated carbon. On the other hand, in acetylene group, only one of its CCC is further connected to CCH, while the other two are duplicated carbon. Therefore, phenyl groups get higher priority over acetylene groups. Step 2. Once the order of the priority of the 4 carbon atom or group directly attached to the chiral atom has been decided, the molecule is then oriented in space in such a way that the group of lowest priority is directed away from us. A good analogy of this situation is the steering wheel of a motor car, with the group of lowest priority representing the steering rod and the 3 groups or group representing by the 3 spokes in a wheel. If it is going from group of highest priority to group of second priority and the group of third priority, the eyes move in the clockwise direction, the configuration is specified. And if it is in the anti-clockwise direction, the configuration is specified as left. The following example illustrate the above procedures. Next is assignment of RS configuration to the Fisher projections. The assignment of RS configuration to Fisher projection of organic compounds involves the following step. First, assign priorities of the first group or atoms attached to the carbon atom. Second, if the atom or group of lowest priorities occupies horizontal position in the Fisher projection formula of the organic compound, then make two interchanges of atoms or group in such a way that the atom of lowest priority group is either placed vertically upward or downward. This is done because by convention in Fisher projection the vertical groups are projected away from us. If however the atom or group of lowest group priority group already occupied the vertical position upward or downward in the Fisher projection of the organic compound, then step 2 is not needed. Step 3, determine the direction of the movement of the ion in going from of highest priority to the group of second priority and then to the third priority, and assigning the group of and assigning RS configuration accordingly. The following examples are illustrated below. Second, assignment of RS configuration to Fisher projection containing two chiral carbon atoms. We have a compound containing two chiral carbon atoms. Four different stereoisomers are possible having the following configuration: 2R3R, 2R3S, 2S3R, and 2S and 3S. Following the steps are discussed in section 3.4.21 above. Each chiral center is separated, assigning RS configuration. Let us assign R or S configuration to carbon second and third in plus tartaric acid. The configuration of plus tartaric acid 2R3R tartaric acid. By knowing the configuration of the stereoisomers, the configuration of the other stereoisomers can be predicted easily by the either below. It must be noted that the direction of the rotation of plane polarized light has nothing to do with RS notations, which only in the direction in which the eye travels when we visualize a molecule held in an arbitrary manner. Thus, RS compounds may be either texturotatory or levorotatory. This can be decided by the golden rule, which is discussed below. Golden rule: assigning priority to the four atoms or group attached to the chiral center. Without making two interchanges of atoms or group, find out the configuration. If the atom or group of lowest priority occupies vertical position in the Fisher projection, then the configuration obtained above gives the actual configuration of the molecules. If however the atom or group of lowest priority occupies horizontal position in Fisher projection, then interchange of configuration from R to S or vice versa. Without making two interchanges, the configuration turns out to be R, since the atom of lowest priority, that is H, occupies vertical position in the Fisher projection. Therefore, the correct configuration of R compounds to be. When without making two interchanges, the configuration turns out to be R, since the atom of the lowest priority, that is H, lie in the horizontal position in the Fisher projection. So therefore change R to S. Thus the configuration of the compound is said to be S. Now simple method for converting flying wedge or 3D formula to a Fisher projection formula. The atom or group shown below the plane of the paper is kept at the bottom of the Fisher projection formula, and the remaining three groups are arranged in the same sequence, and that is in the clockwise or in the anti-clockwise direction as they appear in the flying wedge formula. For example, let us convert flying wedge formula into Fisher projection formula. Since the CH3 group is below the plane of the paper, it is placed at the bottom of the Fisher projection formula, and the remaining three groups OH, H and CH are in anti-clockwise sequence, and they are arranged in the same sequence in the Fisher projection formula that will be shown in the figure number 2. Theoretically, more than one Fisher projection formula can be written for any given chiral compounds. Therefore, to get the most conventional Fisher formula which makes the interchange of two carbon atoms to the chiral carbon atom. For example, the Fisher projection second and third in a flying wedge formula first and second all represent S-lactic acid. Now we will do simple method of converting Fisher projection formula to the flying wedge formula. The atoms group which is at the bottom of the Fisher projection formula is kept below the plane of the paper in the flying wedge formula, and the remaining three groups are arranged in the same sequence as they appear in the Fisher projection formula, keeping one of the atom or group lying on the horizontal axis in the Fisher projection formula above the plane of the paper in the flying wedge formula. Please note that the sequence of all the group atoms in both the formula should be the same. For example, to test whether flying wedge formula actually represent R lactic acid, which which make two interchanges of atoms group in such a way that the atom of lowest priority lies below the plane of the paper. Assigning priorities to the four atom groups attached to the chiral center, you will find formula third and the formula second actually represent the R lactic acid. Now next is geometrical isomerism. Like optical isomers, geometrical isomers are also configurational isomers since they can be interconverted by breaking and remarking of covalent bonds. Further, since geometrical isomers are not mirror images of each other, they are not enantiomers. But configurational isomers which are not mirror image of each other are called diastereomers. Therefore, geometrical isomers may be regarded as diastereomers. Some important aspects of this kind of diastereomers as discussed below. First, geometrical isomers hindered rotation around carbon-carbon double bond. We know that a double bond consists of a sigma and a pi bond. The pi bond is formed by sideways overlapping of unhybridized p orbitals of two carbon atoms above and below the plane of carbon atom. If now one of the carbon atom of the double bond is rotated with respect to the other, the p orbital will no longer overlap and the sigma pi bond should break. But the breaking of pi bond requires 251 kilojoule per mole of energy, which is not provided by the collision of the molecules at the room temperature. Consequently, the rotation about a carbon-carbon double bond is not free, but it is strongly hindered or restricted. As a result, many substituted alkenes can exist in two distinct isomers which can differ from each other only in the relative position of atoms or groups in the space around the carbon. For example, but2ene can exist in two isomers from cis-but2ene and trans-but2ene. Such isomers which have the same structural formula but differ in the spatial arrangement of the atoms or group around the double bond are called geometrical isomers, and the phenomena is called geometrical isomers. Thus, geometrical isomerism is a type of space or stereoisomerism. Now we will do the necessary and sufficient conditions for geometrical isomerism. It may be mentioned here that all the compounds containing carbon-carbon double bond do not show geometrical isomerism. The necessary condition for an alkenes to exhibit geometrical isomerism is that each of two carbon atoms of the double bond must have different substituents which may be same or different. Thus, alkenes of type ABC is equals to CAB and ABC is equals to CDE show geometrical isomerism. However, geometrical isomers are not possible if one or both the doubly bonded carbon atom carry two similar substituents. This is because in each case the two possible configurations are in fact identical as shown below. It is because of this reason that terminal alkenes such as propane, but1ene, 2-methylpropanone and alkenes carrying identical substituents as one of the doubly bonded carbon atom such as 2-methylbutadiene and 2,3-dimethylbutadiene etc. do not show optical isomerism. Now we will do determination of the configuration of the geometrical isomerism. First, on the basis of their physical properties. Melting point. In general, the melting point of trans isomer is higher than that of corresponding cis isomers. In trans isomers, the two similar atoms or group lie on the opposite side of the double bonded. Therefore, their molecules are symmetric and hence packed well in the crystal lattice. On the other hand, in the cis isomers, the two similar groups or atoms lies in the same side of the double bond. Therefore, these molecules are unsymmetrical and hence do not pack well in the crystal lattice. As a result, intermolecular forces of attraction holding the molecules of trans isomer in a crystal lattice are much stronger than those holding the molecules of cis isomers. Consequently, the melting point of trans isomer is much higher than that of corresponding cis isomer. Second is solubility. In general, the solubility of cis isomer is higher than that of corresponding trans isomer. This is due to the reason that molecules of cis isomers are weakly held in the crystal lattice than the corresponding trans isomers, as explained above. Third is dipole moment. In general, cis isomers have higher dipole moment than the corresponding trans isomers, which may have zero dipole moment when the atoms or the group on each carbon atom of the double bonded are the same. This is due to the reason that in cis isomer the two dipoles are inclined to each other at an angle of approx 60 degree and hence a definite dipole moment. On the other hand, in trans isomers the two dipoles act in opposite direction, hence cancel the effect of each other. Fourth is boiling point. In general, the boiling point of the cis isomers are higher than those of corresponding trans alkene. The reason being that the boiling point of isomeric compounds depend upon the dipole-dipole interaction. Since the cis isomers have higher dipole moment than the corresponding trans isomer that is less polar. Therefore, the boiling point of cis isomers are higher than those of corresponding trans isomers. Second, we will do the on the basis of their chemical reaction. First is formation of cyclic compounds. These methods are more dependable on than the physical properties. In cis isomer, the reacting group being on the same side of the double bonded interact with other resulting in the formation of cyclic compounds. On the other hand, in trans isomers, the reacting groups being on the opposite side of the double bond do not interact with each other to form cyclic compounds. Thus, malic acid on heating at 423 readily loses the molecules of H2 to form malic anhydride since the two COH group are near to each other. However, at this temperature, fumaric acid does not form an anhydride since the two COH group are far apart. However, when fumaric acid is heated to 573 Kelvin, it loses a molecule of H2O to the same anhydride, that is malic anhydride, since on hydrolysis it gives malic acid, not the fumaric acid. Second, on the basis of optical priorities for the stereo isomers formed during hydroxylation and brominations of the reaction. The optical properties of the products formed depend upon the stereochemistry of the reactions. Since hydroxylation of alkenes with dilute KMnO4 solution or osmium tetroxide sodium bisulfite treatment is a cis addition process. Therefore, cis isomers give meso products while the trans isomerism will give racemic products. Next is E and Z system of nomenclature. We have been seen above that cis and trans notations can be used without any ambiguity to describe the spectral arrangement orientation of two identical atoms or group attached around a double bond in the distributed alkene. However, in case of tri and tetrasubstituted alkenes, in which there are three or four different atoms or group attached to the carbon atom to the double bond, it is difficult to attain cis and trans notation to the pair of geometrical isomers. To illustrate that, thus let us consider the following geometrical isomers of 1 bromo, 2 chloro, 2 fluoro, 1 iodoethane, in which 4 isomers are attached to the doubly bonded carbon atom. If we say that boron and chlorine are trans to each other, if we can also equally say iodine and chlorine are cis to each other. Therefore, it is difficult to name a substance either as a cis or trans isomers. In order to avoid this ambiguity, a more general system of nomenclature for designating the configurational isomers about a doubly bonded has been developed. This system is called E and Z system, that is based upon the priority sequence rules originally by Chem and PIS to describe the configuration about chiral center in a molecule. The main points of E and Z system are discussed below. First, following the sequence rule, describe the optically active compounds RS in section 3.4.20. A priority order is assigned to the atoms or groups attached to the carbon atom of the double bond. If the atoms or group of higher priority on each other of each carbon atom of the doubly bonded are on the opposite sides of the double bond, the configuration is designed to be E. If on the other hand the atoms or group of higher priority on each carbon atom of double bond are on the same side of the double bond, the configuration is designated as Z, taken from the German word zusammen, that is together. Let us take an example by the two geometrical isomers of 1 bromo, 2 chlorofluorethane, fluoro, 1 iodoethane are. Since we know that atoms of higher numbers have higher priority, iodine is equals to 1 and higher priority Br is equals to 2 at the carbon 1 and Cl get 1 and CF get 2 at the carbon 2. Thus isomers 1 atoms of higher priority I and Cl are on opposite side of the double bonded is designated as E isomers, while the isomer second, while those atoms of higher priority on the opposite side of the double bond is designated as the Z isomerism. Similarly, cis and trans isomers of 2-butane can be designated as E and Z butanes respectively from the above. Next is conformations of ethane. In ethane molecules, the two carbon atoms are connected by a sigma bond. If one of the methyl group in in ethane molecule is kept fixed and the other is rotated about carbon-carbon bond. A large number of momentary arrangement of the hydrogen atom as one carbon atom with respect to the hydrogen atom on the other carbon atom in space are obtained. This infinite number of momentary arrangement of atoms in space represent conformations of ethane. In all these conformations, the basic structure of ethane molecule and various bond angles and bond lengths remains the same. Out of the infinite number of possible conformation of ethane, only the two extreme ones are important, that are staggered and eclipsed conformation. 2D representation of the conformation. The 3D structures can be represented by 2D surface with the help of Fisher projection. One serious drawback of this projection formula is that they represent the molecule in the unfavorable eclipsed conformation. However, while discussing the reactions of the molecule, it is unusually desirable to depict the molecules in its actual staggered form rather than in the hypothetical eclipsed form as shown in the Fisher projection. Therefore, to overcome this difficulty, the conformation of molecules are usually represented by the following three methods. First is Sahout's molecule. There is a simple method of representing three-dimensional four molecule on paper. The molecule is viewed slightly from above and from the right and projected on the paper. The bond between the two carbon atoms is drawn diagonally and is slightly elongated for clarity. The lower left hand carbon is considered to be towards the front and the upper right hand carbon towards the back. The Sahout's representation for staggered and eclipsed conformation of ethane as shown in the figure 3.27. Second, flyway representation. In this formula, the bond connecting the two carbon atoms are drawn horizontally in the plane of the paper. Wedge represents bond lying above the plane of the paper. Ordinary lines are used to denote bonds lying within the plane of the paper, and dotted line stands for bonds lying below the plane of the paper. Flying wedge or dotted line wedge representation for staggered and eclipsed conformation are shown for ethane are shown in the figure 3.28. Third is Newman's projection formula. Newman devised a simple and highly useful method for representing 3D formula on paper. After his name, they are called Newman projection. These projection formula are obtained by weaving the molecule along the bond joining the two carbon atoms. The molecule atom near the eye is represented by a point and three atoms or a group attached to it by the three equally spaced, that is 120-degree radii. The carbon atom farther from the eye is designated by a circle and the three atoms are grouped attached to it by equally spaced radial extension. The Newman projection for staggered and eclipsed conformation of ethane are shown in the figure 3.29. Relative stability of staggered and eclipsed conformation of ethane. In staggered conformation, each of the hydrogen atom on the front carbon atom lies exactly in between each of the hydrogen atom on the back of carbon. In other words, in this conformation, any two hydrogen atoms on adjacent carbon atoms are as far apart as possible. As a result, the repulsion between the electron cloud of sigma bond of two non-bonded hydrogen atom is minimum. On the other hand, in eclipsed conformation, each of the इसने ज़्यादा छोड़ दी, फिर इसने लास्ट तक क्रॉप कर देगी. चल रही है अजब की. Relative stability of staggered and eclipsed conformations of ethane. In staggered conformation, each of the hydrogen atom on the front carbon lies exactly in between each of the hydrogen atoms on the back carbon. In other words, in this conformation, any two hydrogen atoms on adjacent carbon atoms are as far apart as possible. As a result, the repulsion between the carbon electron clouds of sigma bonds of two non-bonded hydrogen atoms is minimum. On the other hand, in eclipsed conformation, each of the hydrogen atom on the back carbon lies exactly behind each of the hydrogen atom on the front carbon. In other words, the non-bonded hydrogen atoms are quite close. As a result, the electron cloud of the sigma bonds of two non-bonded hydrogen atoms repel each other. This raises the energy of the eclipsed conformation relative to staggered conformation. Thus, the staggered conformation of ethane should be more stable than the eclipsed conformation. Experimentally, it has been found to be so. The staggered conformation of ethane is about 12.55 kJ per mole, about 3 kcal per mole, more stable than the eclipsed conformation. The variation of energy of the conformation of ethane with rotation about the carbon single bond as shown in the figure 3.30. The energy difference of 12.55 kJ per mole between the staggered and the eclipsed conformation is in the fact the energy barrier to rotation about the carbon-carbon single bond in ethane. However, this energy barrier is not large enough to prevent rotation. Even at room temperature, the collision of the molecules supply sufficient kinetic energy to overcome their energy barrier. Thus, the two conformations are readily interconvertible. As a result, it is not possible to separate the two conformations of ethane. However, at any given moment, most of the ethane molecules would exist in the staggered conformation due to its minimum energy and maximum stability. Conformations of cycloalkanes. Like alkanes, cycloalkanes also show conformational isomerism. Cyclopropane and cyclobutane are the planar molecules with bond angle of 60 and 90 degrees respectively. But the normal tetrahedral angle in staggered compounds of carbon is 109 degree 28 minutes. Thus, the bond angle in cyclopropane and cyclobutane are quite different from normal tetrahedral angles. This deviation from normal tetrahedral angle introduces considerable angle strain in the molecules of these cycloalkanes. Further, greater the deviation, more strained is the molecule and hence more reactive is the compound. For example, cyclopropane with the bond angle of 60 degree is very strained and hence very reactive. Cyclobutane with the bond angle of 90 degree is less strained and hence it is more stable but reactive than cyclopropane. In cyclopentane, the bond angle is 108 degree. It means that of regular pentagon, which is very close to the tetrahedral angle of 109 degree 28 minutes. As a result, it has very little strain and hence it is quite stable and much less reactive than cyclopropane and cyclobutane. Further, cyclopentane has been shown to have a non-planar conformation, although for all practical purposes it is considered to be planar. On the other hand, Shesh and Moore in 1820 suggested the cyclohexane has two nonpolar or puckered conformation called the chair and the boat conformation, as shown in the figure 3.35. The names chair and boat are used for this conformation because of their resemblance to a lone chair and a boat respectively. It may be noted here that both these conformations are free from angle strain and hence are quite stable and unreactive. Relative stabilities of chair and boat conformation. Although both chair and boat forms are free from angle strain, yet chair form is more stable than the boat form because of the following two reasons. First, in the other conformation, all the carbon-carbon and carbon-hydrogen bonds, that is adjacent atoms on C1, C2, C2, C3, C3, C4 up to C6, C1 are staggered with respect to one another. This can be seen by viewing the molecule along any carbon-carbon bond, say C1, C6 or C3, C4 as shown in figure 3.36. As a result of this staggered nature of the bond in the chair conformation of cyclohexane is not only free of angle strain and toroidal strain but free from steric strain as well. On the other hand, in the board conformation, through on the other hand, in board conformation, through the carbon-carbon and carbon-hydrogen bonds on C1, C2, C3, C4. On the other hand, in the boat, conformation through the carbon-carbon and carbon-hydrogen bonds on C1, C2, C2, C3 and up to C5, C6 are in staggered orientation. Those on C1, C6 and C3 and C4 are in unfavorable eclipsed interaction. As a result of these eclipsed interactions, the boat form of cyclohexane, in contrast to the chair form, has considerable torsional strain as well as steric strain, although, like chair form, it has no angle strain. Consequently, the boat form of cyclohexane should be less stable than the chair form. Second, the boat form of cyclohexane is further destabilized by the steric strain between the non-bonded flagpole hydrogen atoms, H shown in figure 3.37. These flagpole hydrogen atoms are separated from each other by a distance of 1.83 angstrom or 183 picometer, a distance considerably less than the sum of their van der Waals radii of 2.29 angstrom and 229 picometer. As a result, the electronic clouds of these bonds repel each other, thereby further raising the energy content of the bond form. Other conformations of cyclohexane and their relative stability. In addition to the chair and board conformation discussed above, cyclohexane in principle can adopt many other conformations. Of these, only two, twist boat or half chair conformation, are important and will be discussed now. The twist boat conformation can be obtained from the boat conformation as follows. Consider the model of boat conformation, which is shown in the figure 3.38, with the flagpole hydrogen, that is hydrogen A and B, pointing up and look down through the ring. If we hold the C1, C6 bond in the right hand and C3, C4 bond in the left hand and twist the molecule in such a way that C3 and C6 go down and C1 and C4 go up, we will find that the flagpole hydrogens move diagonally away from each other and the two hydrogens on C3 and C6 begin to approach each other. If this motion is continued till the distance separating HA and HB becomes equal to that between HC and HD, that is HA HB is equals to HC and HB bond, a new boat conformation called the twist boat or skew boat is obtained. And this conformation, the non-bonded interaction between the two flagpole hydrogens are at a minimum, and also the torsional strain due to eclipsing interaction on C166 and C3C4 bonds is partially relieved relative to the boat form. Consequently, the twist boat conformation of cyclohexane should be more stable than the boat conformation. This prediction has been verified experimentally. The relative energies of the various conformations of cyclohexanes are shown in the figure 3.39. From the potential energy diagram, it is clear that the chair conformation of cyclohexane is more stable. It is about 29.7 kilojoule per mole more stable than the boat conformation and by about 23 kilojoule per more stable than the twist boat conformation. In other words, twist boat conformation is only 6.7 kilojoule per mole more stable than the boat conformation. The two twist boat conformation are mirror images of each other and circle and Schumann conformations. These are separated by a small energy barrier of about 6.7 kilojoule per mole at the top of which lies the boat conformation. Thus, boat form of cyclohexane is just a transition state conformation, and the two enantiomeric twist bond conformation can get converted into each other by climbing this small energy barrier of 6.7 kilojoule per mole. Unlike the boat and the twist conformation, which are separated by a small energy barrier, chair conformation and the twist boat conformation are separated by a large energy barrier of 46 kilojoule per mole. At the top of this energy barrier lies another transition state conformation called the half chair conformation of cyclohexane. Since this half chair conformation has considerable angle strain of 8.40 kilojoule per mole, torsional strain of 23.4 kilojoule per mole, and the steric strain 14.2 kilojoule per mole, this is the least stable of all the conformations of cyclohexane. Conformation of cyclohexanes. Out of 4 conformations of cyclohexane discussed above, The two most stable conformation, that is chair and the twist boat conformation, are called the conformers of cyclohexane, while the other two, boat and house chairs, are only transition state conformations. The difference in the energy between these two conformers is just 23 kJ per mole. This small amount of energy can be easily supplied by the collision of the molecules at a room temperature, and hence these two conformers are readily interconvertible and hence can't be separated. At the same time, this energy barrier is large enough for each of these conformations to retain their identity. Further, due to the greater stability of chair form, on the average, one molecule is in every 10,000 molecules exist in the twist boat form, while others exist in the chair form. In other words, for all practical purposes, cyclohexane almost exclusively exists in chair form conformation. Axial and equatorial bonds in cyclohexane. The 12 hydrogen atoms of cyclohexane can be divided into two sets, each containing 6. Those hydrogen atoms which lie above and below the general plane of the molecules and are parallel to the axis of the cyclohexane rings are called axial hydrogen atoms, and the bonds holding these hydrogen atoms are called axial bonds. These bonds are usually represented by the letter A. The other set of 6 hydrogen atoms which extend radially outward at an angle of 109 degree 28 minutes to the axis are essentially situated along the equator of the cyclohexane ring are called equatorial hydrogen atoms, and the bond holding them are called equatorial bonds. These are generally indicated by the E. Thus, each of 6 carbon atoms in cyclohexane has one axial and one equatorial bond. Conformations of mono-substituted cyclohexane derivative. The position of the axial and equatorial hydrogens on each carbon atom of cyclohexane ring are not fixed. In fact, these keep on interchanging. In other words, chair conformation of cyclohexane is flexible, that is, at room temperature. One chair form is radially converted into other chair form. This process is called ring flipping, and in doing so, the axial hydrogen in one chair conformations are converted into equatorial hydrogens in the other chair conformation, and vice versa. Both these conformations are identical and hence can't be distinguished. If, however, one hydrogen is replaced by some other atoms of the group, the two forms are no longer identical. Thus, all monosubstituted cyclohexanes, such as methyl cyclohexane, can exist in two conformational isomers, that is, one having the methyl group in axial position and the other having the methyl group in the equatorial position. Because of steric hindrance between the bulky methyl group and the non-bonded axial hydrogen on C3 and C5, axial methyl cyclohexane is thermodynamically less stable than the corresponding equatorial methyl cyclohexane. Such type of non-bonded interaction are called 1,3 diaxial interaction and tend to destabilize the molecule. The extent of destabilization, however, depends upon the size of the substituent. For example, A-methyl cyclohexane is two additional N-butane gauge interaction than the corresponding A-methyl cyclohexane as shown below. This is clear from the above projection formula drawing along C1 and C2 bond that there is one N-butane gauge interaction between the axial methyl and C3 methyl group. Similarly, by drawing Newman projection about C1 and C6, we can show that there is one more N-butane gauge interaction between axial methyl and C5 methyl group. On the other hand, Newman projection formula for the equatorial methyl cyclohexane does not have any such addition N-butane gauge interaction as shown below, since here the E-methyl and the C3 or C5 methyl are in staggered or anti-orientation. The E-methyl cyclohexane is more stable than A-methyl cyclohexane by 2 N-butane gauge interaction, that is 2 into 3.35 is equals to 6.7 kJ per mole. If, however, the size of the substituent is large, the free energy difference between the axial and the equatorial conformation is also large. For example, in case of tert-butyl cyclohexane, the difference in free energies of two conformation is 22.6 kJ per mole. Thus, in methyl cyclohexane, about 5% of the molecule are in the chair conformation with an axial methyl group at room temperature. In tert-butyl cyclohexane, on the other hand, only about one molecule in 10 to the power 4 will have an axial tert-butyl group. Therefore, it can be said to exist virtually exclusively in the chair conformation with the tert-butyl group in the equatorial position. Difference between configuration and conformation. The term configuration should not be confused with the configuration, although both represent the space arrangement of atoms or group within a molecule. Whereas the various conformation of a molecule can be easily interconverted simply by rotation about a single bond, the different configuration of a molecules can only be interconverted by breaking and making of bonds. In other words, the energy of difference between the various conformation of a molecule is very small. This small amount of energy can be easily supplied by the collision of the molecules at room temperature. As a result, the conformations of a molecule are readily interconverted and hence can't be separated. For example, staggered and eclipsed conformation of ethane cannot be separated. A configuration, on the other hand, characterizes a particular stereomer of a compound. For example, in cis-2-butane, the two methyl groups are on the same side of the double bond, while in trans-2-butane, the two methyl groups lie on the opposite side of the double bond. In other words, cis-2-butane represents a particular stereoisomer of 2-butane. Similarly, trans-2-butane represents another stereoisomer of 2-butane. Thus, cis-2-butane and trans-2-butane are configurational isomers of 2-butane. As already discussed, because of the hindered rotation about the carbon-carbon double bond, the energy difference between them is quite large, that is 251 kJ per mole. This large amount of energy cannot be supplied by the collision of the molecules at room temperature. As a result, configurational isomers can't be readily interconverted. In other words, configurational isomers have independent existence and hence can be separated. Like geometrical isomers, optical isomers are also configurational isomers. For example, R minus lactic acid and S plus lactic acid can be interconverted only by breaking and remarking of covalent bonds, which requires around 400 kJ of energy. These optical isomers also have independent existence and hence can be isolated. Thank you and have a cheerful day.